Okay, so now we're going to be talking about the second derivative in graphs. So let's start out with the definition of concavity. So concave up means that the first derivative is increasing, and concave down means that the first derivative is decreasing. So what that basically means is if you had a function that you wanted to look at, and you already had the plot of the first derivative, you could see areas where the first derivative may be increasing over a certain interval. And over that interval, you would see the slope of your graph, your f of x graph, start to increase as well, because it's f prime of x is your slope of your graph at each particular point. And so you would see it go from what it's initially at for its slope to something that has a greater slope later on. And that's basically the idea of concave up, is that if you had that increasing f prime of x, or that increasing slope, you would see the slope go from one value to a greater value a little bit later on. And so that's the idea with concave up. And similarly with concave down, it's the same idea, but in reverse. You're looking at a slope which is decreasing over time, or which is getting less as you go farther forward. All right, and so the second derivative is something that we can use to sort of explain concave up and concave down. So here's some notation right here at the bottom. So this f double prime of x equals d over dx of f prime of x, which equals d squared y over dx squared. And this third notation here is basically just taking that d over dx operation and just pretending that it's squaring it. And that's more or less where this notation kind of comes from. And it's used in a lot of kind of context for some of the higher math courses, which you may or may not see later on, depending on if you take them. And then there's also the notation for y double prime. And this is just a shorthand, probably the simplest shorthand for the second derivative. Just putting a couple of asterisks there, or not asterisks, but apostrophes, in order to try and indicate that you have the second derivative for some function y. All right. So let's talk a little bit about specifically what concavity kind of looks like and how it's related to the derivative and the graph. So if we have the second derivative of x having a positive value, then our f prime of x would be increasing over time. And our graph of y equals f of x would be concave up. And some examples are like this x squared example, where you would see it coming down and then hitting the bottom, then going up. Or you could see the potential for maybe an inverse, or like an exponential decline. So an e to the negative x graph might represent this decline pretty well. And the third one might be represented by an e to the x exponential growth. And so those are three potential examples that you could see for increasing functions, or increasing first derivatives, or concave up situations. You would also look at f double prime of x being negative, indicating that f prime of x is decreasing, which indicates that the graph of y equals f of x is concave down. And you would have these situations where it's negative x squared, where it's kind of pointing down for that kind of a shape. And then you could also have something that's like the ln of x function, which is curving in sort of this strange increasing but still concave down function, or concave down look. And then this one would probably be best represented by just a negative e to the x function. So a negative exponential function, not an exponential decay, but a negative exponential. And so this would be the best idea to represent this sort of a graph. And those are all examples of concave down or having a negative or downwards concavity. And it basically just means that your derivative is decreasing over time as you move farther forward. All right, so that's concavity. Now let's talk about inflection points. Inflection points are basically values where the second derivative is a partition number. And so this is mainly where you're talking about the second derivative being equal to 0 or having a spot where it's flattened out. Inflection points are noticeable mainly because they separate out where your slope is going to go, or where your second derivative is going to go from a positive value to a negative value. And so they help kind of separate those regions out. And they're not, sometimes they're explicitly given on a graph, sometimes they're not, but you'll notice them after you've been taught what they are. And so now you'll probably see them from here on out, now that you know what they are, and you'll be able to recognize an inflection point on a graph. So here's a potential example. I haven't given the explicit function, but just say that we have a plot of this f of x here, and we're looking at it. We can see that there are 2 points here and here. Both of those represent inflection points. So we can take a look at the sign chart for f double prime of x, and we'll have a concave down section where the function is kind of curving downwards right here. And we'll have a concave up section after the first inflection point where it's starting to pull back up and reaches a positive first derivative even after going past this local extrema right down here. And so you'll reach a second inflection point at this second dot here, which is where the function will become concave down. And then we'll continue on. And this concave down portion then brings the slope from what it was at that point to something which is less as it progresses. And so that's the idea behind this function and this sign chart. And I did want to note that inflection points exist between concave up and concave down portions of a function. And so you'll be able to notice them by looking at the concavity of a particular function and noticing that the concavity changes from either being positive to negative or from being negative to positive. And so that's the end of this section. And I'll see you in the next video for the next one.